Hello, this is Mr. Bradley, and today we're going to talk a little bit about acceleration. We have previously studied objects that are moving with a constant velocity, and that really is the easiest case of moving objects. But in reality, in nature, most things will change their velocity during the course of their motion, and when that happens, we call that acceleration. The technical definition of acceleration is just the rate of velocity change. As with any rate, that basically means we're going to take the change in velocity and divide by the time, which is what this equation says right here. Delta V is the terminology that we use to describe change in velocity. Whenever you see this triangle symbol in math or science, that typically means change. And another way of writing change in velocity is to say VF minus VI. I'm giving you a couple new terms here that you probably haven't seen before. Up till now, we just had a V average, which is the average velocity that something has over a long time interval. But now we have a final velocity and an initial velocity. Of course, that's what would happen when something does change its velocity. So now when you're reading a problem, it's important that you understand, do you have change in velocity? Do you have average velocity? Do you have initial velocity, or do you have final velocity? It really is just a matter of reading the context. Most times a problem will say something like, a car is going 25 miles per hour for 2 hours. Well, that would be the average velocity of the car. In another problem, it might say a car goes from 25 miles per hour to 45 miles per hour. Well, then now I'm telling you the initial and the final velocity. The other factor here involved in this equation, of course, is time. And we just annotate time with just the letter T. That's the time that elapsed while this velocity was changing. Okay, so this is the basic equation for acceleration. One of the strange things about acceleration is the unit that it has. Because you're taking a rate divided by a rate, that actually means that you're going to have two time units in your denominator. The one that we use most often in physics is metric units, which is meters per second. But then you'd also have a pretty common acceleration as miles per hour per second. We think about that in the U.S., particularly when we talk about car accelerations. If I talk about an acceleration in miles per hour per second, then I would be saying that a car might have an acceleration of 8 miles per hour per second, meaning that it gains 8 miles per hour of speed every second that it accelerates. So if it started from rest, in 1 second it'd be going 8 miles per hour, in 2 seconds it'd be going 16 miles per hour, in 3 seconds it'd be going 24 miles per hour, etc., etc. In the world of physics, we tend to use meters instead of miles, and of course our base time unit is seconds. And so we'd have meters per second per second. I like to have a little pause there when I say that because I want to make sure you really recognize that there's a speed and then a time involved in that. Now, there is a crazy thing going on here with this meters per second thing. There's a math rule that says when you have a fraction in the numerator of another fraction, you can combine the denominators, which means meters per second could also be written like this. That and that are the same thing. This is just, I guess, a more clever way of writing it. Well, somebody in history decided that an even more clever way of writing it was to do this. Okay? If you have a seconds times a second, that's a second squared. And so oftentimes you'll hear acceleration said meters per second squared. It's really important you understand that this is the same thing as this. And oftentimes it's typed like this, but we like to say it like this, meters per second. There really is no such thing as a square second. That would be a weird unit of dimensional time, which, as far as we know right now, doesn't exist. Okay, so this equation to describe acceleration is VF minus VI over t. Well, this equation is useful when you're trying to relate these four variables together. If you're trying to relate acceleration, final velocity, initial velocity, and time, that's a pretty useful equation. But, probably the majority of the time you're going to be trying to find one of these other variables, not the acceleration, but maybe the initial velocity or the time or whatnot. Well, it's nice to have this equation rearranged for the different forms. So you could also solve for VF by using this form of the equation. or you could solve for VI using this form of the equation. Or finally, you could solve for time using this form of the equation. Okay, really these four equations are just four different versions of the same thing. And it's kind of nice when you're doing physics problems to save a little time and not have to worry about rearranging them on the spot, but then just have these available for you. So good idea to have it on a note card when you're taking a test. We also have a kinematics equation sheet available on the website that have these rearranged if you'd like to use those. Okay, so one really important thing here as we talk about acceleration is that we're going to assume all accelerations are uniform, meaning that things gain speed at the same rate all the time. That's a pretty big assumption because in the real world, in nature, accelerations aren't uniform. Accelerations usually happen kind of in spurts. If you look at a car's acceleration, maybe a car gets up to speed. In first gear, it gains a lot of speed at first, and then it sort of tails off. And then when you switch gears, the same sort of thing happens. That's probably a pretty familiar feeling that you might have. The black line that I drew there really represents probably closer to the real type of acceleration you experience. But, you know, in the physics problems that we want to solve, we don't want to do that. We want to look at really just uniform acceleration like this. So as we do problems like that, we like to say that we're in physics land. Okay? And physics land is just a wonderful place where all the accelerations are uniform, and there is no air resistance, there is no friction. The sky is always blue, the sun is always shining, the grass is always green, the birds are chirping, there's flowers growing. Everybody's happy. You know, physics land. It's a wonderful, wonderful place. Those are the way we do problems in this class. If we weren't in physics land, we'd have to consider the more real-life situations, which involve calculus. And calculus is a little bit messier kind of math. And, you know, this isn't a calculus-based physics class. So, fortunately, we are doing problems in physics land. Okay? Quick note here. This velocity time graph shows that the velocity increases over time. It is increasing at a constant rate. This is the initial velocity. And then this point is the final velocity, as I read it from the graph right here. Okay? Well, if I look at the rate of that velocity change, I'm really looking at the acceleration. And that means that the slope of a velocity time graph is acceleration. That's a pretty big deal. We talked previously about how the slope of a position time graph is velocity, and now we know that the slope of a velocity time graph is acceleration. That's something that we'll probably use from time to time down the road. Okay, so let's do a sample problem. This problem has what's the acceleration in miles per hour per second of an object that goes from 25 miles per hour to 48 miles per hour in 4.2 seconds. As I do problems in physics, it's really important that I go ahead and just write down the givens that have been given to me. That helps me identify the equations. So in this problem, the initial velocity is 25 miles per hour. That's how fast the car is going before it starts moving. The final velocity is 48 miles per hour. That's the speed that it has at the end of its acceleration. The time that it took to do that is 4.2 seconds. Okay? I'm trying to find the acceleration of the car. That's what I'm looking for. Well, I normally would take this list of givens and unknowns, and I would go to my list of physics equations to figure out the right equation to use. And, you know, fortunately, I just gave you this equation, so it should be pretty fresh in your mind. I'm going to use A equals VF minus VI divided by T, and I'm going to solve for my acceleration. Now, right now is the time when you stop and you look at your units and you go, are things going to work out the way I want them to? I have velocities in miles per hour, and I have times in seconds. If I find this acceleration, it's going to be miles per hour per second, which is what I wanted. That's very important. If this was some other unit, maybe I'd asked for meters per second, then I would probably have to do a conversion up front. But I gave you an easy one here first. So I can go ahead and use these numbers just as they are. I'm going to take 48 miles per hour, and I'm going to subtract 25 miles per hour. And I'm going to divide that by 4.2 seconds. When I do that math on my calculator, I get an acceleration of 5.47619, ... and this is miles per hour per second. Up here, I told you to round to the nearest tenth, and so just following those guidelines, I'm going to round this to 5.5 miles per hour per second. Those are the same thing. Okay. What this answer means is that as every second goes by, the car goes 5.5 miles per hour faster, which is a pretty reasonable acceleration given these guidelines. This car is already moving and it goes up to a faster speed, and usually when that happens, you don't necessarily have as much acceleration as you would as if the car was at rest. Okay, let's look at another example with acceleration where you have to solve for another variable that's not acceleration. In this problem, we're actually looking for the final speed of something after it accelerates at a certain rate for a certain amount of time. So we have some different variables this time. One of the important things here to recognize is that in this particular problem, the object starts from rest, which is kind of nice because then that means that VI is equal to 0. This is the rate of acceleration. Now, it says right here a rate of 9.81 meters per second, so it's pretty obvious. But sometimes the information is a little bit more inferred than that. And so if that's the case, I really recommend just focusing in on the units. Look for the units that go with the number, and that'll kind of tell you what the variable is. So in this case, the rate of acceleration is 9.81 meters per second. And then the time is 2.5 seconds. Again, I'm looking at the unit to really tell that that's the time that the acceleration was occurring for. As you read problems in physics, it's really important that you know what the numbers represent and if they apply in the situation in question. Right now we're just seeing like simple one-step problems, but there's going to be plenty of problems where there's 2 or 3 steps to them, and some of the information applies to step 1, but it doesn't apply to step 2. So that's where the reading comprehension piece comes into play. You really have to read the problem well to be able to understand when to use what values. Well, anyway, I'm looking for the final speed of this thing. So the final speed is going to be the initial speed plus the acceleration times the time. And because the initial speed is 0, that makes this equation much easier to solve, because now I can say basically 0 plus 9.81 meters per second times the time, 2.5 seconds, and I'll be able to find my answer. Now first, I need a quick check. Our unit's going to cancel out, and so if I look at this time times this acceleration, that seconds will cancel out one of these seconds, which will leave me at a final speed in meters per second. And this problem didn't say to do it in meters per second. That was a mistake in the problem. But that answer will give me a final speed in meters per second. So I'm pretty comfortable with that. So now all I'm going to do is just calculate this with my calculator and find out what I get. When I do that, I get 24.525. Up here I told you to round to the nearest tenth, so this is the tenth. 25 is going to round down, so this is just going to be 24.5 meters per second. So what I just found here was that if something accelerates at that rate for that much time, this is going to be how fast it's going after that time. Okay, so the last thing that I need to talk about in this lecture is how the sign of acceleration works with the sign of velocity. In physics, positive and negative indicates the direction that things are going. So if something's moving in the positive direction, we say it has a positive velocity. And if it's moving in the negative direction, we say it has a negative velocity, which, positive typically might mean that something is going to the right if it's positive, or up if it's positive. And again, I'm talking about the sign of its velocity here. If something is going in the negative direction, we might say that it has a negative velocity, or if it's going down, we might say that it has a negative velocity. Well, depending on the direction of motion, then the sign of acceleration says a lot about if the object is speeding up or slowing down. Don't just think that positive acceleration always means speeding up. That statement is true if you're talking about moving in the positive direction. If you're moving in the positive direction, then positive acceleration does mean speeding up. But if you're moving in the negative direction, positive acceleration actually means slowing down, because the acceleration is going against the direction of motion. Pretend that an object is moving to the left, but yet accelerating to the right. Well, that would then make the object lose that negative velocity. That would make the object slow down, if you will. Also, the same thing is true about negative acceleration. Negative acceleration does not always mean deceleration. That's true if the object's moving in the positive direction. But if the object was moving in the negative direction, then a negative acceleration would actually mean it speeds up. That's because the acceleration is reinforcing the direction of velocity, so it would actually gain velocity in that direction. Oftentimes people want to know, how could something be moving in one direction, maybe with a positive velocity, yet accelerating in the opposite direction, which in this case, that would be a negative acceleration. Well, this negative acceleration occurs because there's actually a force that causes that acceleration. Now, we're taking a little bit of a step ahead. We'll study this much more in depth when we get into our force unit, but we really can't avoid that right here. If something's moving in one direction, but yet there was a force acting in that other direction, so the force that acts in this direction would technically then be a negative force because it's going against the direction of motion, which was positive. Well, this negative force causes this negative acceleration. The same thing would be true if something was moving up with a positive velocity, but yet there was a negative force acting down on the object. Well, that negative force is going to cause a negative acceleration. And so this negative acceleration against the direction of that positive velocity is going to make the object slow down and stop. And then if that force continues on, it actually might make the object turn around and go in the other direction. We'll see that a lot more with problems as we go throughout the course of this class. So the main thing I guess I want you to think about is that these definitions are really dependent upon the direction of motion of the object. So this chart really serves as like a handy-dandy sort of reminder, if you will, to try to decide if a positive acceleration means speeding up, or if it means slowing down, or if it means gaining speed, or if it means losing speed. Perhaps that's perhaps better terminology. Okay, well, the last thing to add to this lecture is just this little bit here at the very end, and that is because we're always assuming uniform acceleration in these physics problems that we do, we kind of have to do that if we want to keep the math relatively simple. Then, this statement here that I'm showing is true. If something is accelerating uniformly, that means it gains speed at the same rate every increment of time. Well, then you can actually calculate the average velocity by taking the initial velocity and adding it to the final velocity and dividing by 2. This is really just like calculating a true average. And that works as long as we assume uniform acceleration. This graph kind of shows that. This graph shows that there's an initial velocity at the very beginning and there's a final velocity at the end. And it's gaining speed at a constant rate. Well, then therefore the average velocity really just kind of falls right in between here, like so. And then, well, if that average velocity then represents the whole motion, then you really can develop a whole other equation. This is really just d equals v average times t, which was one of the first equations we learned in this class. But now I can substitute in vi plus vf over 2 for v average, and now I have a new equation that relates distance vi, vf, and t, and of course this equation can be rearranged for different variables. All right, well, that was a lot for the first day of acceleration. I hope that this helped to give you some insight that you don't get from just reading notes by yourself. Good luck solving problems, and you might want to tune in for part 2 of the acceleration notes, where we will give you another equation that you can use.